Thank you all very much for coming after lunch, making it out for us today. We're going to talk about microbial challenges in facilities. I would like to leave you with some practical tools and understanding. And to do that, I'm going to pull in some data from a Water Research Foundation study, which has actually been made public, so you can look it up yourself, and also some internal school data that we have. Let's go ahead and start with just an ideal situation where we have a municipal system with good water quality, a good strong residual passes through the meter into a facility where it maintains that water quality and residual. In this scenario, the pipes are just a means of conveyance. But of course, overnight, sometimes we lose all of that water quality. We lose the chlorine residual. And that's what this talk is about today. We're going to talk about ways that we can work with systems that struggle in this way. So why is it? Why does it lose the chlorine residual? Well, unlike a means of conveyance, the piping inside of a facility is often more of a bioreactor, where the microbes on the pipe wall, where they go through their life cycle of growing, eating, producing waste, protecting themselves, and dying, will go ahead and change the water quality, especially water that's been stagnant in its presence. And we see this in real situations. Here are 4 schools in the same district. And the water coming into the facility, these 2 charts, if you can't read it, is copper on the left and chlorine residual on the right, with blue being entering the building and red being the worst fixture inside of each building, and the 4 buildings across the bottom. So we see a massive uptick in copper as a result of the building plumbing, and we see a significant drop, massive drop in the chlorine residual also. So let's go ahead and talk about the chlorine residual first. And there's really 3 ways in which the chlorine residual can disappear in a building. It can come from reactants that are dissolved in the water. It can come from the inorganic chemical reactions on the chemical scale that's on the pipe, but it also comes, and probably predominantly in these situations, from the biofilm on the pipe wall, because that is what grows back with any amount of stagnant water. Let me introduce this Water Research Foundation study. So this is study 4586, and it's optimization of phosphorus-based corrosion control chemicals using a comprehensive perspective of water quality. The principal investigator is Abigail Cantor, who also is a co-author of the American Waterworks Association Manual 58, which is Corrosion Control Manual Practice. And my connection is that all the studies that I'm showing today, I'm a tool manufacturer. Like, I make tools, I design tools, chemical tools, and those tools have been used in these studies. That's the connection. All right, so in that Water Research Foundation study, there is Campus E, which actually has some of the cleanest water of all of the studies that we will look at. And the nice part about this particular campus is it's a full system. It has water treatment all the way which supply all the buildings, and it has a history where in 2006 they added a new well and an iron removal filter, and they ended up seeing leaks, pinhole leaks in their copper water piping all throughout the system. There was a study upon this, and where they found, actually let me just show that real quick. The new filter wasn't working properly. That was kind of expected. They could see that. But they also found high microbial populations at every pinhole leak that they evaluated. And they weren't really looking for that. And so the recommendations were probably what you've seen before. Don't flush the water lines, clean out the piping, don't let the water stagnate, and maintain a residual. But like a lot of these efforts, they weren't really well funded. And so 6 years later, the leaks were worse, and the attention was greater, and the need for intervention was greater. But here's the kicker. So this particular campus, when you measure the microbial activity on the bulk water, actually was the cleanest in all the systems that were part of this study. So it doesn't really scream biofilm problem. In fact, the even even though the pipes were still perforating, they're still seeing pinhole leaks. So what was done was, instead of measuring the bulk water, they went ahead and measured the wall instead. And that's where we found some of the heaviest, thickest biofilm in the entire study. So we have a situation where we have the cleanest water, but we have the dirtiest pipe in the same building. And it was, to give you an idea of how skewed it was, about 98% of the microbial activity was on the pipe wall, where only 2% was being sloughed off into the water. So it's a situation where the biofilm really, depending on the situation, either tells you it's there or it doesn't, based on how much it will slough off. In the lead and copper rule, there's a 6-hour stagnation period. And these 5 systems, these are the 5 facility systems. There were municipal systems that were also part of this study. But in the facility systems, we see the 2 cleanest, the systems with the cleanest water were System F and System E, the first 2 on the left. System E is the one we're predominantly talking about. And the microbial activity increased between 9 and 15-fold between those 2 systems just in 6 hours. And then with the systems that were more contaminated, significantly higher, 100 times to 300 times microbial growth. And we see intermittent flow of just a few hours is a significant growth condition in many cases. Biofilm is a way for these microbes to protect themselves, and there's a variety of reasons why they form, but they also form specifically to protect themselves from a chlorine residual, from the toxins. And they pull together not only organic materials, but also the chemical scale, the iron, the lead, the copper, the manganese. And then when there's disruption, they let them go in the form of particulates. Probably other places today, you've heard about biofilm being in various places in the building, specifically with stagnant water or with large surface areas like the softener and the GAC, or in the hot water system. So these are good places to look if you're looking for it. But I'd like to just bring up the lead and copper rule when it comes to dissolved versus particulate metals in the water. So the lead and copper rule is modeled after the idea that lead is a solubility problem. It doesn't discuss particulate metals at all, or those that come from biofilm or chemical scale. And so when we look at a pipe as it actually exists, we see that there are minerals, there's microbes, there's nutrients coming in, and we have biofilms, and we have chemical scales, and they're intertwined, interlaced. And then coming out, we have discolored water, odor, E. coli, Legionella, disinfection byproducts. These are all multiple consequences of the interface between the pipe wall and the water. So if you can manage that one interface, you can affect a lot of these parameters all at the same time. And biology has multiple ways to form dissolved metals by attachment acids or acidic waste that it produces, or it can produce solubilizing waste. Actually, as part of the life cycle of the bacteria, can pull lead or specifically copper out of the wall and result in very high levels of copper, or even electron theft by taking iron bacteria, for example, taking electrons from the metal surface. So the key point here in this talk is about particulate lead and understanding where it comes from and how to find it, how to understand it. And so that comes about when there are changes in the water system where the biofilm reacts, temperature swings, flow changes. Any kind of treatment change is also a nutrient change, because chloramines, for example, have nitrogen, orthophosphates have phosphorus. These are nutrients. And even in our cleanest system, which was actually a municipal system, not a facility system, but the cleanest system still had 50% of the lead reaching customers in a particulate form. That means that lead was not following the rules of the lead and copper rule, or the chemistry of the lead and copper rule. It was being accumulated in biofilms and being sloughed off in particulates. This particular study has a large amount of data, and particularly in areas where the water was stagnant. And so in these situations, there was no correlation found between the chemistry of the lead and copper rule and dissolved lead. And there are a few more insights on this slide. But also another one that I want to point out was that one campus actually cut its phosphate dose in order to essentially try to starve the biofilm. And it effectively did that, but the phosphate actually increased, or the phosphorus increased months later as the biofilm was dying and sloughing off that material. I mentioned Campus F along with Campus E, and these are both similar in that they have good quality water with biofilms. And often we think of biofilms as an old building problem, but on this campus, they built a brand new building, and before the building was even put into service, the water system had biofilms with pitting as well in the copper pipes. And so I should also mention that both of these facilities were also completely compliant with the lead and copper rule during this entire time. So compliance doesn't necessarily equal a healthy plumbing system. So here's what the lead and copper rule does measure. It measures total lead. But total lead can be broken up into two different components: the dissolved lead and the particulate lead. And you can't determine the difference between the two with that required test because it's preserved with an acid. So we have to have a way in order to determine which one is, how much is particulate and how much is dissolved, because the conversations are completely different. If it's dissolved, then you can effectively deal with it with maybe a change in the chemistry associated with the lead and copper rule. But if it's particulate, we're dealing with scale and biofilm, and so it's a hygiene problem. It has to be cleaned out, physically cleaned out. It's important to note that biology can also create dissolved lead and copper, like we saw in the earlier slide. So here's the kind of the key takeaway, and that is, in order to better understand the system and what's going on, if you are able to filter the sample and have two samples, basically split a sample between and measure both for lead, but one of them is filtered, then you can get a total and dissolved lead number, which the difference between the two is the particulate lead. So you can begin to understand if the problem that you're dealing with is dissolved, or is it coming from scale and biofilm. There are 4 additional cheap instruments that also see biology inside of facility water. And ORP is probably the most useful tool. It's just a meter, it's easy to use, and if you measure 300 millivolts or better, it's generally considered inhospitable to microbial growth. Turbidity, you would measure that because we are looking for those particulates. And it would show up in a turbidity measurement. ATP is your measurement of microbiological activity. So if you have a situation where there is a lot of sloughing off, you can easily see that. And ammonia and nitrate will reveal if you have nitrification cycling going on. And this is especially important in copper pipes because copper is a part of that process. In a building, there are really 4 places that you would need to look weekly in order to get a good understanding of the health of your system. The water meter, the softener. The reason the softener on the outlet of the softener is because you have such a high surface area there. Also the far cold tap, because you've gone through all of the piping. And then the far hot tap, because you're measuring, again, a lot of pipes or the recirculation system. And in most cases, you're going to lose your residual in that hot water. And if you really want to understand what area of your building is causing the problem, you can take a sequential 1-liter profile just by filling up 1-liter bottles sequentially and then equating the volume of those bottles with the amount of pipe that they represent, and then matching those up with the pipe material. And you can basically walk your way back through the building all the way into the water main and the service line to see where the problem is occurring in your system. So a building hygiene kit for helping to maintain a healthy building and also to repair a healthy building, repair a building that's struggling. You have the opportunity to lower water age through flushing or rotating the softeners, or often buildings will have the fire line that supplies the fire system along the same service line as the drinking water, so that service line is much larger than it needs to be for drinking water, which can cause a problem. So if you can get those split off, that's a big win for you. And then there's monthly maintenance of blowing down the water heater. This is where a turbidity meter is actually quite helpful, so you can see when you've fully cleaned out that water heater tank. High velocity flushing, this is where you want to do some remediation, some air scour and pigging, and if you want a force multiplier on there, you would use a chemical assist, and this is of course the product that I manufacture, so I'll throw the logo on there. So back to those 4 schools. Basically 1 week from start to finish, this was an intervention, and it required an aggressive chemical treatment and a few air scours. But look at the difference. We went from copper levels in the thousands down to well within below the action level, and the chlorine residuals returned back to where they were. But there are a few things that you need to know going in before you start a hygiene program on a building that is struggling. And that is, when you are cleaning, you're releasing debris. And it is very likely that the problem is going to get worse before it gets better. And flushing a system with lead can also increase the dissolved lead, even though you're removing the particulate lead from the system. And any kind of disruption that you have in flow or in treatment will also affect the chemical scales in the biofilm, causing possible upsets as well. And if you do have pinhole leaks, it's very likely that the crud that you're trying to get out of the pipe is what's actually plugging those holes. So you may see some pinhole leaks result just from your treatment. But these are temporary situations, and they need to be managed and controlled to get through it. It is possible to use turbidity, and the chlorine residual is kind of your speedometer, using a residual to see the progress you're making, but turbidity to make sure that you're not doing it too quickly. And so this is what I'd like you to take with you, and that is to ask for dissolved and total on your lead counts. Putting an ORP meter or turbidity meter on the far hot tap can be very effective in order to see what's going on. The monthly maintenance of your water heater and blowing down that tank can tell you a lot about what's going on in the system. And make sure you're flushing the areas that are not getting used. And probably the best measure of how healthy your building is measuring the residual at both the entry point and the farthest fixture. You can get a feeling for what kind of appetite your building has for chlorine residuals. So the thrust of this talk is to basically say that you don't have a lead problem, you have a pipe wall problem. And that's essentially what I have for you today.